Hello everyone, my name is Fabrizio from 20 Squares, and today I wanted to talk a little bit about a technique, more of what we do or stuff like that. So, okay, this is the current state of the ecosystem. I'm going to be honest, I think that basically every auditor in this room has had to shovel enough shit to know that, we live in a time of often badly set specs, badly implemented code, and auditors are basically called to fix that. If you, listen around and look at what many people have to say about methods to improve the situation, at least to me, it really feels sometimes that the proposed solution looks a bit like this. Like many people, propose some fancy new cryptographic primitive that is going to solve everything and stuff like that. But in the end, at least my feeling is that sometimes what we still lack is a deep theoretical understanding of, some of the things that go on in basically the smart contract and blockchain world more generally. So for what I experienced, one of the worst parts where a lot of errors basically pop up are around interfaces. Interfaces here is a very loosely defined concept. For instance, a contract calls another contract, bad stuff happens, multi-chain interaction, bad stuff happens, off-chain, on-chain interaction, bad stuff happens. It feels like a lot of times when you have something of type A and something of type B interacting, bad stuff can happen. Now, basically, if you ask to programming language theory experts and people that do that kind of kink, they will tell you, well, we invented type theory to solve some of these problems. That is true, but sometimes that's not enough. So in that picture, you can see, for instance, a very well-defined type, a very well-defined other type, a very creative type conversion between one and the other that, yes, works, but it really feels like duct tape again. So if we had a formal solution to solve this, basically the kind of thing I wanted to talk about in this talk is exactly that. There is a mathematical theory that is called category theory that I feel is very underrepresented in our community. Basically, category theory was invented in the 40s, and it's the formalism on which nearly all of the biggest achievements of mathematics in the last 50 years have been built upon. And the idea is that category theory is the superglue of mathematics. It really makes you able to describe what happens when things interact. So, in this image here, for instance, we have the basic object, one of the basic objects of category theory, that is the concept of a functor. So the idea is that a category is basically a mathematical object made of objects and structure preserving maps between them. If you are versed, that could be types and functions between them. It could be sets and functions. It could be groups and group homomorphisms. It could be, topological spaces and continuous maps. The list can basically go on forever. But the idea is that you can package the idea of a particular structure, a particular flavor of structure into the notion of a category. And now you can basically have the notion of a morphism between different categories that is basically a kind of coherent transformation that allows you to morph this structure to map it to another kind of structure. So that's exactly what happens there. I have a notion of objects down, A, B, and C, and transformations between them that can be composed. And the idea is that I also have another category upstairs, and a functor is exactly a map that allows me to map objects into objects and transformations into transformations in a coherent way. Now, you could be like, okay, interesting, but what do I do with that? Well, Funnily enough, basically in the last 20 years or so, category theory has been used extensively to model things that are kind of not really related with mathematics. So, I mean, yeah, joking, they are, but not as much as you would expect. So, for instance, this thing here, this kind of a weird bunch of dots and stuff, it's a pictorial calculus that allows you to do quantum mechanics. Basically, these kind of pictures can be manipulated in a very formal way, and they allow you to reason about quantum mechanical systems, and they allow you to instantiate quantum algorithms and quantum protocols without touching linear algebra at all. Like, you can basically play like a little kid with these things, and you can verify and prove properties about quantum stuff. How does it work? Well, it works because there is category theory underneath that basically says to us that we can consistently mapping all the linear algebra that we usually need to do quantum computing into these pictures. So the idea is that you do all this giant work, it took like 20 years or something, and then you can hide it, and you can basically let kids playing with these things, and they are happy, and you can do quantum computing. Similarly, here we have a picture of basically the bread and butter of what we do at 20 Squares. This is a graphical calculus that allows you to do game theory. And in fact, those things depicted there are basically the prisoner dilemma. The idea is that you have two players that are the two triangles. They basically perform an action. This action gets piped into a payoff matrix. And the payoff matrix basically gives back the payoffs to the players. Again, you can follow this as a picture, but the funny thing is that, again, there are categories in the back that basically tells you, yeah, these things compile to games in the traditional sense. And I kid you not, basically we implemented this thing. You can compose these little Lego bricks, and then you can basically push a button and compute the equilibria of this game. So yeah, in here we have, again, other categorical stuff. I'm not really going to talk in depth about this, but basically, I guess that the gist of this talk is that, yeah, category theory is really the math of composition, and studying it in depth will, you know, really turn your understanding of mathematics and how interfaces work, interface between things, upside down. So that guy in the picture is a guy that did a ton of category theory, and I mean, you see how it started and now it ended. Probably that's not a good example, but yeah, I mean. And yeah, so all in all, it's true, theories are just theories, but when you have a good abstraction about your problem, I think that really helps you understanding what's going on. So yeah, I think that's it. I just wanted to point out to you that this thing existed, and look it up on Wikipedia if you want. I'm done. Thank you.
Thank you.